In this video, we're going to talk about transformations of graphs. Transformation is just a word that means change. So we're going to talk about different changes that we can make to the basic graphs that we've been discussing. If you have not yet graphed the basic graphs for yourself or taken a look at which function has which shape, I want to encourage you to maybe stop or pause this video and go and do that first. Get comfortable with the basic graphs and then come back and we can talk about making changes to them. Okay, we're going to make 3 different types of changes to these basic graphs. The first one is called a translation. It's essentially a shift. And the idea is that we are going to take the shape of the graph as it is and move it either up, down, left, or right. So I wanted to give you a couple of examples of that and then talk to you in general about our goal in this section is to make a connection between what we see in the equation and what we see in the graph. Okay, so the first 2 examples that we're going to do involve basically the parabola, right? The y equals x squared, that's the most basic squaring function. And I think you've graphed this one before, so I just kind of left these points filled in. If you were to choose to make this graph, you can use the standard x value, -2, -1, 0, 1, and 2. Plug them in for x and square them to get the y values. And we should get this parabola shape. This is the basic graph. There are no changes made to this graph. When we talk about comparing, we are comparing with this basic graph. Okay, so what if we make a change to the equation? This actually, I think, comes from your book in this section. What if we want to graph y equals x squared minus 2? As it turns out, we can make the graph with the same standard set of x values. And when we plug these x values into the function, we're going to square them and then subtract 2. So we would put in -2, square it, that would become 4, and then subtract 2. So we would get 2. And we could do that with all of these, right? -1 squared would be 1, -2 would be -1. 0 squared would be 0, -2 would be -2. 1 squared would be 1, -2 would be -1, and 2 squared would be 4, -2 would be 2. So if we plot these points, -2, 2, -1, -1, 0, -2, 1, -1, and 2, 2, you can still see that same parabola shape. What kind of shift has it made from the standard parabola? Can you see that it's gone down by 2? Okay, so when I put a -2 at the end of my function, it's going to shift that shape of that graph down by 2 units. Okay, we're going to, in this section, talk a lot about the equation compared with the graph, like we said. And so when we describe a shift, it's 2 things you want to list. You want to list the direction, which in this case, it's shifted down. And you want to list by how many units, which in this case, it's moving down by 2 units. Okay, so just some general information I want to add at the bottom here. This is a vertical shift. Vertical meaning it could be up or down. And the way a vertical shift is going to appear in the equation, it's going to be an amount or a number added or subtracted outside the basic function. Okay, so that -2 is outside of the x squared. It's sort of tacked on to the end. And so when that's the case, when it's on the outside, it's going to be a shift up or down. And the up or down shift is just like we would expect it to be, right? A -2 that we have in this example shifted it down. If it were a +2, it would have shifted it up. Okay, so you can kind of predict that. When we have a vertical shift like we do here, it's the y values that have changed. So if you compared this to the basic function, I still am using the same x values to make the graph, but the y values have changed, and that has caused a vertical shift. Okay, let me give you another example. This one looks similar, but it is different, okay? Now we have the x -2 in parentheses squared. And so that's going to cause a different type of shift. Can you guess which way this parabola is going to shift? Okay, let's graph it and find out. All right, so in order to make this graph, we're going to need x values that are different than the standard set. So you can almost think about choosing an x value that is greater than the basic one, so that when I subtract 2, I get the same x value I would have used. That sounds a little bit complicated. And in the basic graph, 0 is in the middle. So if I want to have a 0 after I subtract 2, I'm going to put a 2 in the middle. Eventually, we're going to talk a lot about how to graph parabolas, how to identify the vertex, and we're going to put that vertex point right there in the middle. So this should tie into that once we've talked about that as well. So 2 is the x value for the vertex. And I want to pick points around 2. And by doing it this way, when I subtract 2, I get back to that -2, -1 set of x values. Okay, so I can plug these in. 0 minus 2 would be -2 squared. This is going to give me 4. If I plug in 1, 1 minus 2 would be -1 squared, would be 1. 2 minus 2 would be 0. Squared would be 0. 3 minus 2 would be 1 squared, which would be 1. And 4 minus 2 would be 2 squared, which would be 4. So if I plot these points, I have the point 0, 4, 1, 1, 2, 0, 3, 1, and 4, 4. And same thing's true here. You can see this parabola shape. It looks just like the basic shape, but it's been shifted. Can you see how it's been shifted? Okay, this one is shifted to the right by 2. And the same thing's true here. We're listing the direction and the number of units that it's been shifted. Okay, so in general, this would be a horizontal shift. Horizontal would be a shift left or right. And when the graph is shifted horizontally, we're going to see an amount or a number added or subtracted this time inside the basic function. So in this example, notice the -2 is inside the parentheses and inside the squaring. The squaring is giving us the shape, and that -2 on the inside of that squaring is going to shift it left or right. Now the left and right shift is opposite of our intuition. So we would think if I'm subtracting 2, I would shift it to the left. And if I were adding 2, I would shift it to the right, but it's actually the opposite of that. So because I have a -2 inside the parentheses, I had to choose x values that were 2 greater than I would normally choose in order to counteract that -2. And because I chose x values that were bigger, it shifted the graph to the right. Okay, so however you choose to remember that is fine. Usually I just think, okay, look, the left and right shift is opposite of what I would think. Okay, another way you could think of it is it's always going to be x minus the shift. So in this case, it's x -2. Think of that 2 as being positive and shifting it in the positive direction. Okay, there are lots of different ways you can choose to remember it. The two things I want to, kind of drive home is number 1, it's inside the function, and number 2, it is opposite of what we would expect it to be. Okay, so we've looked at 2 examples here that are for a parabola, but really you could apply this to any of the basic graphs that we have looked at. You could do the absolute value v, you could do the square root shape, the cubing shape, right? Any of those functions would have these same effects. When we make this change to the equation, whether it's outside or inside, we will see the same changes in the movement of the graph shape. That is a translation. Okay, so we said we're going to look at 3 changes. Translation or a shift was the first one. The second change we're going to look at is a stretch or a shrink. Okay, and that's usually what the book uses. That word shrink, I don't like that word. I like to use the word compression. And oftentimes in the book, it talks about both vertical and horizontal stretch and shrink. And I like to keep it to just one to reduce confusion. So we're only going to talk about the vertical type. Vertical stretch, so I'm stretching my graph up like a piece of taffy. Or vertical compression, so I've set something like a heavy book on top of my graph shape and it's sort of squashed it down. Okay, so the way a stretch or a compression is going to show up in the equation is we'll have a number out front of the function that is multiplying the function. And so I want to kind of explore with you what kinds of numbers will cause a stretch and what kind of numbers will cause a compression. So I'm going to use the parabola again. I didn't do a super great job of making this so that it would fit on the screen. So we'll do this for the moment. Okay, so we're going to graph 3 graphs. One will be the basic graph. Let's go ahead and put those points on there so you can have that as a reference. So this is the same basic graph we started out the video with. We have the standard set of x values here, and when I plug them in and square them, these are the y values I get. Those points are going to make the standard parabola, so let's put them on our graph here. because this is the standard parabola, the basic one, this is the parabola that we're going to compare the other graphs to. And we're going to graph all three of these on the same grid today so you can see how they compare to one another. So this would be the basic graph. Okay, then we're going to change, we're going to put a number that's being multiplied here times the x squared. So we're going to try out a 4 times x squared and a 1/4 times x squared. Now since these graphs aren't shifted at all, the same x values can be used to make the graph. So the x values are really not going to change. Notice the number in front that we're multiplying is on the outside of the function. Anytime I make a change to the outside, I'm going to see that the y value is what has changed. So I'm going to use the same x's, but I'm going to get different y's. So if I plug these in, I'm going to square first. -2 squared would be 4. That's what I got over here. But then I'm going to multiply by 4, and I get a y value that is 4 times greater. Same thing for all of these. So if I put in -1, squared would be 1, but I'm going to multiply by 4, and so I get 4. 0 is going to stay the same. That's sort of our rock point that keeps the parabola situated in the same location. 1 would give me 1, but I'm multiplying by 4. So I get 4. 2 would normally give me 4, but I'm multiplying by 4, so I get 16. Okay, now I didn't make a grid big enough to show you 16. All right, so -2, 16 would be way up here off the paper even. All right, so just you'll have to visualize that. The next point we had was -1, 4. We still had our point at 0, 0 in the middle, and then +1, 4. So hopefully you can see by multiplying by a number that was larger than 1, 1 would be like what we have in the standard graph. By multiplying by 4, I get a parabola shape that is a little bit skinnier, and it's been stretched upward, stretched vertically. And the way that we would describe that in words is we could say that there is a vertical stretch by a factor of 4. Okay, so you can see that being stretched, and we get a shape that looks like that. So what happens if we put in a 1/4 multiplied by x squared? Same reason, same x's. Okay, we're going to square them and then multiply by a 4th. So if I square it, I would usually get a 4, but then I multiply that by 1/4 and I get 1. For -1, I square it to get 1, and then I multiply by 1/4, so I get 1/4, or 0.25. Okay, 0, 0 is my low fixed point there. 1 is going to give me 1/4. And if I plug in 2, 2 squared is 4, and then I multiply by 1/4, and I get 1. Okay, so now I want to graph those points. So let's put them on our grid. So I have -2, 1, -1, a 4th, 0, 0, 1, a 4th, and +2, 1. It is still a parabola, a bowl shape, but it is a lot wider It's almost as if we have set something heavy on the graph and it has sort of pushed it down to be this, I'm going to say, compressed shape. Okay, so by multiplying by a number that was smaller than 1, again, this y equals x squared, you can put in an implied 1 there. If I have a number that's smaller than 1, I have a vertical compression. Or if you want to use the word shrink, you can. So this one is, I should have said this is vertically compressed, okay, by a factor of 1/4. Okay, so to make sort of maybe a more general statement, I'll do that at the bottom here. We said that we're going to see a stretch or a compression if we have a number out front. We're using the variable a to describe that, multiplied by your function. If that number, and now I have the absolute value bars here because I'm not really concerned about whether that number is positive or negative. That does something else. We'll talk about that next. But just the number part, irregardless of the sign, the number part, if that number part is larger than 1, then I have a vertical stretch. But if the number part out front is smaller than 1, I should not have the equals bar there, just a less than, not equal to, okay? And we're just looking at the number part, so it is going to be bigger than 0, sort of between 0 and 1, which is a fraction, like a fourth or a half or 3/4, something like that. In that case, we're going to see that the graph has been vertically compressed, or it is a vertical compression. Okay, now we did our example here with the parabola, again, so that you could see that all side by side. The same would be true if we use the absolute value v shape or the square root graph or any of those basic shapes that we have talked about. Okay, so this would be the second type of change, vertical stretch and compression. And so this is what it would look like for a parabola. The last change, transformation that we want to talk about is a reflection. So a reflection forms a mirror image of a graph across a line. It's thundering outside, it's about to rain. Okay, so I want to do the same kind of analysis here. I want to kind of graph 3 graphs together so you can see how this reflection happens. I like to do this, demonstrate the reflection with the square root of x graph, because I think that one makes a really nice picture and it gives you a really good idea of what is happening. So let's start with the square root of x. Do you remember what x values work best for the square root? Usually I get you guys to say perfect squares because those are really convenient, and today we're going to make use of that. We're going to use perfect squares, but remember also the numbers have to be positive. 0 is the smallest number I can use and take the square root and get a number out so that it's not undefined. I actually get a number for y. So I'm going to put in my perfect squares, right? 0 counts, 1 counts, then I have 4, 9. The next one would be too big for our grid, so I'm going to stick with these 4. And when I take the square root of these numbers, square root of 4 is 2, square root of 9 is 3, of course. Okay, so let's graph those on this grid so you can see the basic shape that we're comparing to. I have 0, 0, 1, 1, 4, 2, and 9, 3. And the shape is sort of like a half of a parabola on its side. So this is the basic square root function. Okay, so we're tracking a reflection. So a reflection is going to happen when we add a negative either inside or outside of the basic function. Okay, so we want to look at those two possibilities. What if I put the negative on the outside? What happens? And what if I put the negative on the inside? What happens? Let's start with putting a negative on the outside. We've already sort of said that if I put or make a change to the outside of the function, I'm going to make a change to the y values. So that means for number 2 here, I can actually use the same x values that I used for my original square root of x graph. I can use those here. What's going to be different for this number 2 is I'm going to take the square root of these numbers and then I'm going to apply the negative. So that doesn't really affect 0 because negative 0 is still 0. When I take the square root of 1 is 1, apply the negative, I get negative 1. Square root of 4 would be 2, apply the negative, negative 2. Square root of 9 would be 3, apply the negative, I get negative 3. Okay, so when I put a negative on the outside, the y values become negative. The effect that that has on the picture, same kind of phenomenon happens here. 0, 0 is sort of my rock point. It's sort of fixing the location of my graph. But now my y values are negative. So I have 1, negative 1, 4, negative 2, and 9, negative 3. So all of my points that were once above the x-axis are now below the x-axis. So by putting a negative on the outside, and this is something I always have to think really hard about, the y values change, and that makes the graph reflect from above to below the x-axis. So it's reflected over the x-axis. Okay, let's take a look at graph number 3. If I put a negative on the inside, we said any changes I make to the inside are going to affect the x value. Sometimes that looks like a shift left and right. This time it's going to be a reflection. So if I have a negative here on the inside, what kind of x values do I need to use that are going to work in this function? Because when I plug a number in, I'm going to apply a negative to it first and then take the square root. Or you could say, instead of saying apply a negative, you could say I'm going to change the sign first. Maybe that's a better description. Okay, so what's going to work here is negative numbers. Again, 0 is our rock point that doesn't actually change. Just to prove that to you, you're like, what? Negatives? Okay, let's check out negative 9. If I put in negative 9 for x, the negative I have in my function is going to multiply with the negative 9 to become a positive 9. And then it's positive, so I'm able to square root it, and that's going to give me a 3. Okay, and I could do a similar thing for all of these, so we could fill these in. Oops, I should have done this in black, but you get the idea. So I get the same y values that I would have gotten from the original function, but I had to use different x's to counteract the negative on the inside. And by doing that, I'm going to see in the graph a reflection. So I have the same center point, but now I have a negative x. So negative 1, 1, negative 4, 2, negative 9, 3. It's the same shape, but I have a mirror image of my original shape across the y-axis. So this one is reflected over the y-axis. Okay, so now you can see if I place a negative on the outside of a function, it's going to affect the y values and it's going to reflect the shape over the x-axis. If I put a negative inside the function, it's going to affect the x values and it's going to reflect the shape over the y-axis. If you wanted to write that down sort of in a more general way, use f of x as your function. F of x could be any of these basic graphs that we've looked at, right? I used the square root of x here, but you could use the x squared, x cubed, any of those, cube root, okay? If I put the negative on the outside, I'm going to see a reflection over the x-axis. If I put a negative on the inside of the function, right, within the squaring or within the square root or within whatever kind of function I'm using, I'm going to see a reflection over the y-axis. Okay, so I'm going to stop here and make this a part 1 for this video. This sort of gives you the basic idea of these 3 transformations. And I will make a part 2 to this video to give you a couple of extra examples, different ways that you can apply these things kind of combined together in one example. All right, these are some really big ideas in this section, so I hope you'll take the time to look these over and practice as much as you can with these graphs in lots of different problems so that you can get a handle on how these transformations changes to the equation make changes in the graph. Good luck.